This tutorial aims to introduce you to the integral test, a tool which allows you to draw conclusions about the convergence of a series by studying the integral of some particular function instead. This will be useful in cases where that integral is easier to handle than the series in question. We start by making a simple observation. Suppose we have given a real-valued function f that is defined on the interval from 1 to infinity with 1 included. That means f maps all real numbers that are greater or equal to 1 onto some real number. That function f now gives rise to a sequence of real numbers. This sequence is given as follows. The first sequence element a1 is defined as f of 1, that is, the value the function f takes on at 1. The second sequence element a2 is defined as f of 2, a3 is defined as f of 3, and so on. In general, we can say that an is defined as f of n for every integer n greater or equal to 1. For example, let us consider the function where f of x equals 1 over x for all x greater or equal to 1. Then this function gives rise to a sequence with the following elements: a1 or f of 1, which in our case is 1, a2 or f of 2, which is 1 over 2, a3 or f of 3, which is 1 over 3, and so on. In general, we have that an or f of n equals 1 over n for all n greater or equal to 1. So overall, we have linked the function 1 over x to the sequence 1 over n. Now we can state the integral test. Let f be a continuous, decreasing, and positive function. Here positive means that f takes on only values that are greater or equal to 0. Then the series taken over the sequence f of n converges if and only if the integral from 1 to infinity taken over the function f of x converges. Otherwise, the series taken over the sequence f of n diverges to plus infinity. For example, we can use the integral test to show that the harmonic series diverges to plus infinity. Clearly, the underlying sequence of the harmonic series is the sequence 1 over n. Now we need to observe that this sequence is linked to the function where f of x equals 1 over x, because then we have that f of n equals 1 over n for all n greater or equal to 1. Furthermore, it is well known that the function 1 over x is continuous. One can easily check that it is decreasing, and finally it is clearly positive. Now, by the integral test, we know that the series taken over the sequence 1 over n converges if and only if the integral taken over the function 1 over x converges. So in order to understand the harmonic series, it is enough to understand this integral. So let us calculate that integral. It is the limit for t going to infinity of the integral from 1 to t taken over the function 1 over x. Now the integral of 1 over x is the natural log of x. This yields the ln of the upper bound t minus the ln of the lower bound 1. Since the ln of 1 equals 0, we are just left with the following limit. But as t goes to infinity, so does ln of t. This shows that our integral does not converge, and so by the integral test the harmonic series does not converge. But in a case of non-convergence, the integral test indicates divergence to plus infinity. In particular, we now know that the harmonic series diverges to plus infinity.